So I'll just revise whatever we have seen yesterday. It was a half half wave controlled rectifier in which there is input supply to a transformer, then there is HWR, there is gate control circuit, we have seen R load for R load. So the input is here, Vs. Output is taken here, V0. Then we have also drawn the load current. Let's say it is I0. And also the voltage across HWR VT. So now the waveforms. So always we draw supply voltage, source voltage first. Whatever is Vs here, that has to be drawn here. And then the V0 output. हाँ ऐसी तक क्लास चलो So the HCR will be forward bias for positive half cycle and it will conduct after some delay. So some part of the half cycle will be appearing in the output. This is the output. So initially SCR is in forward blocking state and afterwards it will be conducting. So forward blocking state, conducting and then reverse blocking. In this way, in the next positive cycle also it will start conducting after some delay. Current, current follows voltage, just the magnitude is different. Current is also same. And voltage across diode. So initially it will be in blocking state, so some voltage, positive voltage will be appearing across it. And then the negative voltage will be appearing. So for this part here, there will be a negative voltage. So it blocks voltage for this time and also this time, this period. Then we have to calculate the performance parameter of this. So for this waveform, we have to calculate what is the one cycle from 0 to 2 pi. It is the one cycle. So to calculate performance parameters, we have to calculate average area of this waveform over one cycle, then RMS value for voltage current both, and then we can calculate the different parameters. So starting with average value. So for our reference, I will draw the waveform here. This V0. So first we want to calculate the average value or DC output voltage. So let's say it is VDC. It is area of wave divided by the period. Using integration. So here the waveform is present only during alpha to pi. So we have to integrate equation of the waveform, that is Vm sine theta, between alpha to pi. So you will get area. So instead of V0, integration of V0, and I'll directly substitute Vm sine theta d theta. With respect to d theta, we have to calculate. So this will give us the area, and dividing it by period. Period is 2 pi. So here Vm is maximum value. It is a constant. So constant will be coming out of the integration. So Vm by 2 pi, the term will be here, and then it will be just integration of sine theta. So it will be a minus cos theta, then upper and lower limits. After substituting the limits here, what we'll get is Vm by 2 pi into bracket 1 plus cos alpha. So this is the DC value. This is the average value of the waveform. So similarly, current, if we draw current for R load, it is same as the voltage waveform. What is the difference? Its maximum value is given by Vm by R. So if we draw or if we calculate DC value of the current, what will be that one? It will be just Vm by R into bracket 2 pi. I'll just change this to I. So if this is current waveform, purposefully I'm just I0. If it is I0, then given by Vm by R sin theta. So DC output current will be IDC. Again, area of the wave divided by period. So it will be Vm by R. Here also Vm by R. And here also Vm by R. So only this is the difference. For current, now once again we have to calculate RMS value for the voltage. So again the same waveform, and we want to calculate RMS value. So DC output, instead of DC output, now we have to write RMS output voltage will be VRMS. VRMS is squared area and under root. Only this is the change. So for the integration now, we have to square the equation, integrate within the same limits. So you will get squared area. So now again Vm is constant, so it is coming out of the integration, and it will be just a Vm square outside the integration divided by 2 pi. This is all under root. Okay. So Vm square as it is outside the integration. Now we can't directly integrate sine square theta. Instead, we have to substitute for it. So substituting it by 1 minus cos 2 theta by 2, then we can integrate. So it will be Vm square by 4 pi now. Because this 2 is also constant, it is coming out. So Vm square by 4 pi. This whole is under, I use another color so that it will be very easy to identify. I'll use black color now. So it becomes Vm square by 4 pi now. I hope you all are having pen and paper and you are also writing it down. So here just integration of 1, it will be x, that means theta. Okay, this is with respect to d theta. So integration of 1 or constant is theta, and for sine cos 2 theta, it will be sine 2 theta by 2. The limits this whole under root. Just substitute the limit. So it will be Vm square by 4 pi as it is here. Then into bracket upper limit minus lower limit minus again putting upper limit and lower limit. So finally you will get, I'll directly write down the simplified one now, Vm by 2 into bracket 1 by pi into bracket phi minus alpha plus sine 2 alpha by 2 whole under root. So taking this Vm by 4 outside the, you can say under root. So that's why it is just Vm by 2 now. Phi is there inside. And here the value of sine 2 pi by 2, okay, that is calculated. So what is value of sine of 2 pi? It is 0. Okay. So this is sine wave. Of pi. Pi is also 0 and sine of 2 pi. Again, it is coming to 0, isn't it? Sine 0 is also 0. Sine pi 0. Sine 2 pi 0. So from the sine wave also we can easily, okay, write down the value. Sine 2 pi is 0. So only these terms are there. So this is the RMS value of the voltage. Now if I also write it for current, then what will be the difference? Just R term will come here. Vm by R. Okay. The rest of the things are same. Now next will be the DC output power, PDC. So PDC is given by VDC into IDC, that we know. So average value of voltage into average value of the current. Just writing it down. Next parameter is PDC. PDC is VDC into IDC. So that what is VDC? It is Vm by 2 pi 1 plus cos alpha. Then what is IDC? It is Vm by 2 pi R into bracket 1 plus cos alpha. So the 1 by R will remain outside. So this comes out to be 1 upon R into Vm by 2 pi 1 plus cos alpha. So there are two brackets. So they will get multiplied. Therefore, bracket square. Then the PAC. PAC is PRMS into IRMS. Just now we have calculated the RMS value. So that also is Vm by Vm square by 4 pi R outside the bracket and into bracket pi minus alpha plus 0.2 alpha and 2 alpha by 2. Now rectification efficiency will be output of one input. Okay, it is difficult to simplify, so we'll just keep it as it is. So while solving numericals, uh, we will be directly calculating the values of PDC and EAC and then directly taking the ratio. So it will be easy at that time. But currently all are variables, so very difficult to simplify it with the variables. So just keep it as it is. So in the numerical, what could be given? So there are only two unknowns here in this equation, alpha and maximum value. And obviously, either of it is given on any one of these two is given, generally given, and then we have to calculate the another one. So we have calculated the AC power. Okay, now we are going to calculate the power factor. So input power factor is power delivered to load divided by input volt ampere. Power delivered to load, that is nothing but the PAC. PAC divided by input voltage, that is VS, into RMS. So PAC we have already calculated here. Therefore, directly input power factor will be equal to PAC which is VM square by square by 4 pi R. to bracket phi minus alpha plus sine 2 alpha by 2 divided by Vs. Vs is maximum value upon root 2. It is a sinusoidal voltage. So Vm by root 2 into IRMS. So we know what is IRMS. We have already calculated. So it is Vm by 2R 1 upon 5 pi minus alpha plus sine 2 alpha by 2 under root. So, so here is the full bracket and here it is under root. So after division, here in the numerator we will get the same bracket and it is just under root. Rest of the values will remain as it is. Then there is Vm square here, so it will get cancelled. So just now strike out Vm square R. Then there is 2, this 4. All this will get cancelled and there will be just 2 root 2 or root 2 remaining. And here this whole bracket will be going and this will remain. So I'll write down the final answer now. The input power factor will be 1 by under root 2 into pi minus alpha plus sine 2 alpha by 2 under root 2. Okay, so this is the performance parameter of half wave controlled rectifier. Now I'll see the effect of load on the operation of controlled rectifier. On controlled rectifier, effect of type of load on controlled rectifier. So just consider this simple circuit now. It is R load. So for R load, whatever is the output voltage, same is the output current. Difference is the magnitude. So here the magnitude is Vm, and here the magnitude is Vm by R. And if it is RL type of load, if it is RL type of load, what happens? So L is inductance of the load. Now we all know that inductor stores energy in the form of magnetic field. Now, as soon as we trigger the HWR at alpha and voltage is applied, it is suddenly applied. There is a jump. So this jump is opposed by this jump is opposed by current or inductor. So current will not follow the voltage. So current allowed is slow rising. So the conduction will start at this point, but the will not be current will not be suddenly rising. So it is slowly rising current. So for the period for which the voltage is positive, current is rising. Afterwards, the voltage will go to zero. So what's the situation? What will happen? So as input voltage has gone to zero, the HCR also should stop conducting. So HCR is trying to shut down, but the inductance will always release the energy. It will not it cannot store the energy because it is in the form of magnetic field around it. So this magnetic field will collapse if we suddenly cut the circuit. And collapsing means there is large di by dt with this inductor. So a very large voltage will appear across inductor. So when the input voltage goes to zero, the HCR start to commute, try to commute, but this inductor will release the energy and it will keep the on state as it is. So what is the effect of inductance? It is actually extending the operating or time of the current. So the inductor will release energy by maintaining current in the same direction. And as inductor loses energy, the current is dropping. So it is like this. Now, we can say that during this period, inductor is charging. And during this period, inductor is discharged. So during this period, inductor is charged. And for the remaining period, discharging. Now the point where the current is going to zero is called as the so this point is beta. Okay. At this instant the current goes to zero. Where it is starting? It is starting at alpha. So this is the effect of inductance on the inductance on the performance of the converter. We'll see the waveform in detail in the next lecture. Is there any doubt?